So now we have a vector field in R3. What does that mean? Every location in R3 is assigned a particular vector. And so now everything's in 3 dimensions, right? So the vector that you get will be a 3-component vector. So what does the general formula for that look like? Let's see here. So R of x, y, z now. So now this is your location in R3, is your input thing. And that spits out a vector, and each one of the components of the vector is a function of x, y, and or z. So the x component of the vector could be a function dependent on x, y, and or z. Same with the y component, same with the z component. So this is what? This is a 3-variable vector valued function. 3 variables is a location in R3, and then the function spits out a vector, in this case a 3-component vector. And so we get a vector field in space instead of like the ones we saw last time in the plane. So just like the examples before, these examples, all the components are either plus or minus x, plus or minus y. Now we could also have plus or minus z, then plus or minus 1 and 0. So these are my only choices for these visual type kind of figuring out what the field is. We're going to restrict the choices to plus or minus x, plus or minus y, plus or minus z, plus or minus 1, and 0. Okay? Although vector fields could have much more complicated formulas for their vectors than this. In terms of a visual type problem, we'll keep it simple. Okay? So this first one. So is there any component that we can know right off the bat here, looking at this vector field? Is there any component?
It's like y is always positive.
Okay, well, y is always positive. That's good. That's a good first. So this g, x, y, z will be some kind of, yeah, anything else that we can know right off the bat?
Z is 0.
Yeah, do you see the z component of every vector is 0? So that's a good start. So that's a good start for this one. Let's write that down. So we're going to have something, something, and 0. Well, that's sure nice because now that reduces this problem back to an R2 vector field. And if I can come here and I can come and take a look at my xy plane. And can we figure out what we got here? So now I'm looking straight down on the xy plane to figure out what the x and y components are. So someone said y is always positive. Let's look at the y components. So it's always positive, and is it changing? So let's see here. Are those y components staying the same or varying?
Looks like they're always the same.
It looks like they're always the same, and then we can go this way too. So we want to go in both directions. It looks like no matter where you are in this field, the y component is always kind of the same positive value, which would mean that, what is it?
Would just be positive 1.
It looks like, yeah, it's looking to me like no matter where we are, the y component of all these vectors, whether you go in the x direction or in the y direction, just always stays a positive constant. Our only positive constant that we have to choose from is 1. Okay, making good progress. So now I got to figure out is what is the x component of these vectors.
Looks like it changes with y. It gets more positive when y gets more positive.
All right, so let's see here. So drawing out the x components. Changing with y. What about if you change x, do they change?
Not at all.
No, they don't change, right? So going in the x direction, the x components don't change. But going in the y direction, the x components change, which makes us think that the x component is a function of y. So something either going to be plus or minus y. So, yeah, it looks like in the x direction, the x components stay the same. So our only choices are plus or minus y. So which is it?
It'd be plus y, because as y is positive, x becomes more positive, and as y is negative, x becomes more negative.
The x component of the vector, yeah. So yeah, as the y location becomes more positive, the x component of the vector kind of tracks with that, right? It gets more positive. So it looks like maybe this is y1, 0. So this, I should erase all those in there, though. So let's see if it's right. I've got it right here. That's it. y1, 0. Any questions on this first one? So these examples are really good because they really force you to understand what a vector field is. Every location, the formula tells us that this, so this is like R of x, y, z. Here's my vector function that at any location, the corresponding vector at that location will be, the x component will be the y coordinate. The y component will always be 1 and the z component will always be 0. That this determines what vector you have at the point x, y, z.
So Professor,
yeah.
what types of like applications can this be used for? Like,
so I showed you like fluid fields, electromagnetic fields. I showed you a bunch of examples in the lecture last time.
Oh, okay.
Yep. But yeah, like fluid field is like or electromagnetic field are the two most, like whether it be wind field or an actual like liquid field like water, or showing you the direction and magnitude of flow. And then the electromagnetic field is another really important one.
For sure.
Okay, so let's do another example of this. No, is this number 2? That's number 2. Here we go. So here's one. I'm going to figure out what field is this. So we'll watch it spin a little bit, and then we'll try to see what we can figure out. Again, the choices for each component are plus or minus x, plus or minus y, plus or minus 1, and 0. All right, so let's take a look at here. I'm looking at the YZ plane. This is looking right at the YZ plane. What does it look like? Is there any?
0.
Okay, nice. So you see that the y components of the vectors in this case, there's no left or right differential to these vectors. They're all kind of up and down, and no component in the y direction. So I think that's a good start. Y0. And then let's stay looking at this plane. What do you see about... So x is coming... We really can't see the x component in this view because x, we're looking right down the x-axis, so there's no way to tell what the x component is, but maybe we can tell what the z component is. What is the z component of these vectors?
Z component, y increases, the magnitude of z increases.
Careful, this is x coming out at us, this is y to the right, and this is z up, right? We're looking down the x-axis at this.
Oh, I'm sorry.
That's okay.
It's proportional to y, the z component.
So as you change in the y coordinate, z changes or not?
No, z stays the same, but it looks like y. It looks like the like z increases like nevertheless of whatever like y is, or whatever X
Z
is.
seems to increase with itself, so as
Yeah,
it
Z
Yeah,
is Z.
increases, it becomes larger in magnitude.
Basically.
Yeah, so z is not changing with the z components of these vectors are not changing with y. So
Yeah.
that's been said a few times. Z components of the vectors are changing with what?
Z.
Z.
With respect to Z.
Z, right? As you go up in z, the z component of the vector increases. And then as you go down in z, in negative territory, the z component gets more negative. So what do we say? What do we know?
Z is Z.
Z is z, right? Z is z. Move in positive, z is positive and getting more positive. The z components of the vectors get more positive. And when z is negative and you go down, the z components get more negative. So z is just simply z. Okay, let's take a look. So all we got left is x to figure out. So we need a different view for that. So let's look, maybe we can figure that out looking at the xz plane. So now I'm looking down at the xz plane. And we're asking, what we're interested in is the x components of these vectors.
They look constant.
So let's make sure going in both ways. So going up and down it looks constant. What about going left and right?
Still looks constant.
Yeah.
Constant.
Yeah, they're all constant.
Yep, the x components are just the same. So
1.
It would be positive 1.
yeah, so that's the only choice I gave you for positive constant. So maybe this is the vector field 1, 0, z. Let's take a look. Got it. There it is, 1, 0, z.
Can you go real quick at why y is equal to 0?
Sure. Let me just give us a different view here. So you wouldn't be able to see it in this view because we're looking right down the y-axis. So you can't see any change in these vectors in the y direction. But if I go and spin and look at the yz plane, so this is now looking right down the x-axis. Y is left and right. So what are the left and right components of these vectors?
Oh, I see. It's 0. There's no change.
Yeah, all of the magnitude of the vector seems to be up and down, and there's no part of this vectors that are showing left or right change.
Professor?
Yeah.
A question. So basically, like the item that you put inside the vector, this 1, 0, c, basically the item that you put in the y position for this, like this 0, what caused you to put this 0 here is basically like what happens to each of these vectors at these locations. Basically, my question is like, assuming there's like something happened in the y, then your answer would then be whatever happened and you put it in here.
So a vector function gives you a vector for every location. So the formula for the vector field tells you what the vectors are as a function of where you are. So I'm looking at these vectors and I'm seeing that there's no y component to these vectors.
I see.
All of the strength or all of the
Yeah, I understand now.
yeah, all of it is up and down. And there's nothing left and right, so that means a y component of 0. All right, one more example like this. Maybe a little bit harder. This one. Here we got one. I'll let it spin. You can watch it spin a little bit here. And we'll see what we come up with. So really the key to these is to look at individual views in individual planes to see if you can find out something. So we'll start with the YZ plane and see if we can make any conclusions to the YZ plane. So now what happens here is the way that the software is showing us is that The brighter, do you see that there's brighter pink and then more grayish, less bright pink?
Yeah, I can see
The
that.
brighter pink ones are the ones in closest to us, like the most positive X territory.
Oh.
And then they turn more gray as you go in the negative X direction or away, like away into your screen. So this is Y and this is Z. And so the real brightest pink ones, the ones pointing up the most, those have the greatest X value. And then the ones that are the most grayish have the least X value, or like the most negative X value. All right, so can we, so what about either Y or Z? Can we figure out what either Y or Z is?
Looks like y is 1.
Yeah, do you see that like all these vectors, like this is a good example right here. Do you see all those vectors have the same Y component? That's all the Y component for all of them is like this. It's that much, and so it looks like to me also that the Y is 1. So now what about the Z component? So that the Z component would be the up and down, in this view, the up and down component of these vectors.
Looks like x.
Yeah,
it
it looks like
depends
it
on X.
depends
Good.
on X, not Y.
Right, because, so I told you this bright pink one is the one that's furthest, closest to us, or most positive X coordinate. And then moving further back, you'd have this one. I just don't want to draw them on top of each other. And then moving further back, you'd have like a slightly negative X. And then moving further back even further, you'd have a greater negative X. So it looks like the Z component is the same as the X coordinate. Oh, sorry. That's not right. The Z component is the same as the X. That goes here then. So then we just need to get a view for X and see what we can find out here. So does that make sense? Why Y is 1 and Z is X? And we can verify these in different views, right? So this isn't the only view we can figure out what Y and Z is. We can look at other views to check that. All right, so let's see. So let's do the, say, I don't know, XZ. Let's look at XZ and see what we get from XZ. All right, now I'm looking right down the y-axis now. And so this now is X. And that's Z. So let's confirm now that the Z component is the X coordinate. Sorry, I'm drawing the wrong thing. The Z components. Do the Z components look like the X coordinate?
They sure do.
Yeah, right? As you move further in that positive X direction, your Z component matches that. It gets bigger positive. And then as you move in the negative X direction, your Z components get bigger negative. So that looks like a check. So all we have left is, what are the X components of these vectors? And maybe this view is going to be able to tell us that.
Looks like Z.
Yeah.
So now I'm drawing X components.
Yeah, it looks like Z.
As you move in the X direction, it looks like the X components stay the same. But if you move in the Z direction, it looks like the X components increase, Z positive, and the X components get bigger negative as Z gets negative, so I think it's Z. So I think this one is Z1X, as some of you are saying. Got it. Okay, so again, every location is assigned a vector according to the formula, which these were the formulas we were figuring out. Okay. Any questions? All right. So let's talk about we're going to kind of advance the conversation here now. Okay, so here's a review. A vector field is the idea that every blank in a coordinate system has a blank associated with it.
Location and vector.
He says every location in a coordinate system has a vector associated with it. Do we all agree with that?
I agree.
Yes.
I agree.
Good. All right. And so then, remember the components of a particular vector are determined by the location, and these component functions define the field. That's what we were figuring out. We were figuring out what were the component functions as we were looking at these fields. What were the component functions that define the field? So we've got the R2 version. And so this is location in the plane, gives us a two-dimensional vector. And then location in space gives us a three-dimensional vector, just like the ones we were just working on. So that's just an overview. There's a dipole, like a magnetic dipole vector field. So this would be like, blue would be the positive side, red would be the negative side. So repulsive of electrons here, and then attractive of electrons on this side. So then as you move further away from it, the strength of the field decreases, right? So you have smaller vectors away from the magnet. Okay, so let's talk about, remember the gradient. What was the gradient? Back when we were talking about, this came up when we were talking about directional derivative, right? We said there's, we had, for a multivariable function, a surface, there was lots of different rates of change at a particular point, depending on direction. And then this thing, the gradient, came up. Okay, so let's find the gradient function and explain what the gradient means. So what would the gradient of this function, this is a multivariable, what is this? This is a real valued multivariable function, right? So it spits out a real value, but it's multivariable, meaning there's two or more than one input variable. So what would the gradient field be for this? So remember, the gradient was the vector of what?
The change of f of x and f y.
Right, good, the partial derivatives, right? So we found the partial derivatives, and we made a vector out of it. Remember that? So this one would be what? What would the gradient be for this function?
2x.
2x. And?
2y.
2y. Partial derivatives, right? Partial derivative with respect to x, partial derivative with respect to y. And we said that was gradient of f. And then we could plug in -1, 2, for instance. So the gradient evaluated at -1, 2 was? -2, 4, right? Okay, what do you notice about this right here? What do you notice about this gradient?
It's a vector.
Looks like a vector.
It's a vector.
But
This-
it also
this is a
corresponds
vector.
to a point.
This is a vector. What's this?
That's a vector field because you can plug in any point.
Right, right. So this is a vector field. So when we were doing gradients, we were actually, when you just found the partial derivatives and didn't actually plug in and just leave them as functions, so now we have a vector field. At any value, at any point x, y, there's an associated vector with that point. That's a vector field. And what was the gradient again? So what was this really important concept about, say, this? What is this gradient vector for the point -1, 2? Remember what this meant? For the point -1, 2 on the surface? What did this vector tell us? Who
Is
remembers?
it the shortest distance to like the highest point,
Okay.
the maximum?
Okay. Yep. That's right on the right track. So if we want to say that most directly, so that's kind of indirect way of saying what it is.
A small change in a certain value correlates to that small change in the z value.
Okay. All right.
Like
Yeah. So the gradient.
Magnitude.
Yeah, the gradient gave us what? Gradient gave us the direction and magnitude of oh, someone please know this.
The max rate of change.
Maximum rate of change, right? If you're standing on the side of a mountain, like a surface, the rate of change, the steepness that you encounter if you take a step depends on the direction that you walk. Right? Surface. Here we are. Mountain climbing. Right? Here we are. Where's the little just here? Right, so here's a path, right? If you walk along the path, there's a certain rate of change. But if you walk off the path this way, you have a different rate of change. And if you walk off the path this way, there's a whole nother rate of change. So depending on which direction you go on the side of a mountain, you'll encounter different rates of change. In fact, there's an infinite number of rates of change you could experience depending on the direction you take your next step. There's a direction of 0 rate of change. And then there's a direction of maximum rate of change.
Does the negative gradient give you like the least?
Yeah. So the opposite of the so at this point, -1, 2, the direction you'd walk for greatest rate of change on the surface would be this direction, -2, 4. And then if you walked in the direction 2, -4, you'd be the steepest downhill rate of change. Okay? This is review. So this should be ringing bells. This should be familiar. And then to get the rate of change, it was the magnitude of that vector. So the magnitude of this vector is, I think, square root of 20. So this is actually the max rate of change. The magnitude of the gradient is the max rate of change. And the gradient gives the direction that you would head to encounter that max rate of change. Again, that should all be familiar. So then what would this vector field be? So now we call this a gradient field. It's a field of vectors. So what would it be?
It's the max rate of change for every point for every point.
Right. So it's now like it's like a function of these gradients, right? So for any location, it's telling you, given a location, it shows you the direction and magnitude of max rate of change. Okay, so let's see what my slide says. We already did that. So a gradient field is a vector field of partial derivatives. It indicates the direction of greatest rate of change, and its magnitude is the value of the greatest rate of change at any given point x, y now. So it's a function of gradients, right? This vector field is now a function of gradients. Not ready for that. Okay, so let's look at that one in particular. Let's see here. All right, so let's work through this here. Let's sketch the surface. So this is this one we were just looking at. X squared plus y squared minus 3. So can you sketch that surface? What kind of surface is that?
Wouldn't it be a cylinder?
Okay, I got 1 vote for cylinder. Agree with that?
It's a paraboloid.
Paraboloid, right?
Circular paraboloid.
Z Z equals x squared plus y squared. So a linear equals the sum of squares. That's a paraboloid. And how is it transformed from our reference paraboloid?
It's down 3 on the z-axis.
Down 3, right? So it's going to look like... So we'll just make a sketch here. So the vertex is down 3, maybe down here. But then besides that, it's like our reference paraboloid. Okay. What was our gradient field? So the gradient field, so we could write it like this. What did we say it was?
2x, 2y.
2x, 2y. Can we sketch that? So we'll sketch that in the xy plane. So what does it mean? As x increases, so the x coordinate kind of corresponds to the x component of the vectors, and the y component corresponds to the y component corresponds to the y coordinate. So are we going to get bigger in x as we go this way, and bigger negative in x as we go this way, and the vectors will get bigger in y as we go this way, and bigger in negative y as we go this way. So can you just imagine overall what that will look like? The further you get in the x, the bigger the x component. The further you get in the y, the bigger the y component. So
Would it look like a parabola in both directions?
No, it won't look like a parabola. It'll just look like vectors getting larger and larger away from the origin, pointing out from the origin. Does that make sense? So small x coordinate, big y coordinate, equal x and y coordinate, big x coordinate, small y coordinate. They're just going to be like vectors getting larger, pointing straight out from the origin, and getting larger and larger as you move away from the origin. And then that would be the same in all 4 quadrants. So here's the paraboloid. And then let's sketch the vector field here, 2x, 2y. So that's the gradient field. That's the vector field of gradient vectors for this surface. It's the vector 2x, 2y. How is that gradient field consistent with the surface? How do we see that those vectors are consistent with the surface if they're gradient vectors?
Like a projection onto the plane z equals -3?
No.
Because as the vector is getting closer and closer to, or it's like spreading out, the z is increasing more rapidly.
Further away from, so on this paraboloid, when you get further away from the origin, what happens to the rate of change?
It starts spiking.
Right, so the further away you are from the origin, the steeper the surface is. The closer you are to the origin, what's the rate of change? Like down around the bottom. This is closer to the origin, right? Closer to the z-axis. How about the rates of change here, high or low?
Low.
Low. But the further you get away from the z-axis, the rate of change keeps increasing and increasing. And so how does the gradient field show that? The vectors are getting bigger in magnitude as you move away from the origin. And what about the direction? What would be the direction of max rate of change at any point here? So if you were on this, say you're in a canyon here, you're walking in this canyon, and you're right here. Which way are you going to walk for steepest rate of change? Which way would you walk? You're going to walk away from the z-axis, right? The steepest is going to be if you walked away from the z-axis. If you walk towards the z-axis, you're going to go down the fastest. So if you walk away from the z-axis, you're going to go up the fastest. That's why these vectors are all pointed away from the z-axis, because it's the direction of max rate of change. And then it gets, the function gets steeper and steeper the further away you are from the z-axis, so that's why these vectors get bigger and bigger as you move away. Okay, does it make sense? So you really have to have a good concept of, you know, the gradient itself. The gradient itself. So for instance, let's see. Let me try just one more time here. So say this point 1, 1, or sorry, 1, 2. So here's the point 1, 2 in the xy plane, and then the z value that we get is down here. So this is 1, 2, what? 1, 2, 2. It should be negative. Oh, so sorry. So 1, 2 gives us 1 plus 4, so 1, 2, positive 2. So I'm the wrong way. So actually, when you go 1, 2, then we're actually in here. There it is. Okay, so 1, 2, 2. And what's the gradient vector we get at 1, 2, 2? Is that 4 or 2, 4?
Yeah, so fast.
Gradient vector 2, 4. So here's the point 1, 2. Gradient vector in the xy plane is 2, 4. And what is that showing us? It's showing us that here on the surface at 1, 2, 2, that would be the direction that you'd go up the fastest. Walking away from the z-axis, you go up the fastest. And what would your rate of change be? The rate of change would be? The magnitude of the gradient. Rate of change meaning how much up you go for a change in the horizontal direction. Given any change in the horizontal direction in the direction of 2, 4, the amount of increase in z would be radical 20 times as much as your horizontal change. Rate of change. Change in z over horizontal change.
So wait, does that equation, the magnitude, does that have anything to do with like finding the hypotenuse of a triangle?
No, it's the ratio. It's not the hypotenuse, it's the ratio of, it's the ratio of change in z to change in horizontal.
Okay.
It has more to do with like inverse tangent. It's not the length of the hypotenuse, it's how much up you go for how much horizontal you go.
Okay.
Which is our partial, change in z per change in horizontal in the direction of 2, 4. Now, the gradient field then is a field of a bunch of vectors that give us all that information for every point, right? So the blue field then tells us the direction and rate of change maximum for every point on the surface. Okay, let's look at another one. Maybe this one. Yes. Okay. So here's a surface. Z equals negative x plus 2y plus 3. So we're going to find the gradient at these 2 points. So we got 3, 1, 2, 0, 2, 7. Those are 2 different points on this surface. What's the gradient at those 2 points? So if this is,
Would it just be
so with the gradient, I'm calling the function g. What's the gradient of g? If g is negative x plus 2y plus 3, that's the z coordinate.
negative 1, 2?
Negative 1, 2. So we said that the gradient is a vector field. Is that a vector field? Negative 1, 2? Is that a vector field?
Yeah.
What is the gradient vector at this point, 3, 1, 2?
Negative 1, 2.
It's negative 1, 2 at all points.
Good. Okay, so yeah, at 3, 1, 2, there's that vector, negative 1, 2. And what about at this point, 0, 2, 7?
It would be the same thing.
Same
It
thing.
has a
That's what other people are
vector
saying
of
too.
negative 1, 2.
Yeah. So no matter what point you're at on this surface, the gradient vector is negative 1, 2 for all points, regardless of location now. So can you imagine what that vector field looks like?
All the x components have a negative 1, and all the y components are positive 2.
Right. So what does that mean? What kind of surface is this? Negative x plus 2y plus 3. Oh, please know this.
It's a plane.
That's a plane, right? That's a plane. And what's true about a plane? What is this showing? What do we know about a plane that this is showing us?
Maximum rate of change is always in one direction.
Yep, and it's going to be what? Constant, right? Right. So let's try here. No matter where you are on a plane, there's always going to be, it's going to have the same max rate of change in the same direction. So no matter where you are on this slanted plane, you're going to go to go up the steepest, you're going to go the same direction, negative 1, 2, and then the rate of change will be the same. What will the rate of change be? In the direction negative 1, 2.
It'd be square root 5.
Right. No matter where you are on a plane, you go the same direction for maximum rate of change, and you're going to encounter the same rate of change. So what? This is the three-dimensional version of what? This whole thing is the three-dimensional version of constant rate of change. A plane in R3 is like the multivariable version of constant rate of change. And so the gradient vector is showing us that. The gradient vector is a constant vector everywhere. So we have, no matter where you are in the xy plane, no matter where you are on this plane, the direction and magnitude of maximum rate of change is the same because it's a flat surface. So this is a constant gradient field showing constant rate of change for a multivariable function, and that simply is a plane.